Welcome back, everyone. We are going to continue with our discussion of organic acids and bases. And now we're going to focus our attention on using other methods than the pKa chart in order to assess acid strength. So let's get started. Okay, so we can use pKa values to predict equilibria. Some of you guys have studied the concept of equilibrium. Some of you guys haven't. Basically, an equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. And you can actually tell from the pKa and the Ka values if the products are going to be favored or if the reactants are going to be favored. In order to do this for acids and bases, you're going to look at an acid and base reaction, and you're going to need to find the pKa's of the acid components. Here, water is the acid, and if I look on my chart, water has a pKa of 17.5. On this side, this tert-butanol is the conjugate acid. And if I look for that pKa on a chart, that has a pKa of 18. Now remember, the higher pKa is the weaker acid. So this is the weak acid, and this is the stronger acid. Remember, the stronger acid gives us the weaker base. So this is also the weaker base. So this side is the weak side. This concept that we're just going to discuss is always true in an acid-base reaction. The equilibrium favors the weaker acid and base side. So in order to represent this, the arrow that goes to this side is much larger than the arrow that goes to this side. This arrow is indicating that this side is favored, and in any given reaction, I'm going to have more product than I have reactant. So this would favor the fact that if I wanted to react this base with this acid, I'd actually get the products. If I had the reverse situation and the reactants were favored, because that would be the weaker acid-base side, what that tells me, if the reactants are favored, is that my forward reaction doesn't actually occur. So I can't use those conditions in order to do that reaction. I'd have to find a different way. So equilibrium in the following acid-base reaction lies to the right. This is my stronger base. This is my stronger acid. I really only have to look at the pKa's of the acid. Here, acetic acid has a pKa of 4.76, and ammonium has a pKa of 9.24. Because this is higher, it's weaker. The stronger acid gives me the weaker base. So this is going to lie to this side and only a little bit here. And that's, so these products are going to be favored in this reaction because this is the weak side. That's the side, the product side contains the weaker acid and the weaker base. Equilibrium will lie towards the product, which means this reaction will actually proceed as written. Okay. Just to reiterate a couple of principles that we've already discussed, if my Ka for an acid is 1 times 10 to the 5th, what can I say about this material? 1 times 10 to the 5th is a very large number. Remember, if I increase Ka, I increase acid strength. I already know it's an acid, so I can't say that I know it's a weak base, right? It's an acid, and my Ka is 1 times 10 to the 5th. So that's a large number. I'm going to choose this A answer. It is a strong acid. Again, this is going to give you the answer and why that happens. If I took the pKa of 1 times 10 to the 5th, I would find out that my pKa was -5, which also is another way to indicate it's very strong. So to indicate acid strength using Ka values or pKa values, I'm just looking at the numbers comparatively. Now, what if I don't have that pKa chart, right? What if I don't know the pKa values? I can still assess stability of acids and bases, but here I'm gonna compare the stability of their conjugate bases to one another. So I'm gonna take 2 acids, I'm going to make on paper their conjugate base, and then I'm gonna compare the stability of the conjugate base. Remember, the stronger the acid, the more stable its conjugate base, because the stronger the acid, the weaker the base. Well, bases do not want to react with acids if it's stable. So that would that's consistent with the fact that the stronger acid is going to give me the weaker base, which is going to be more stable. So when an acid loses that proton and forms that conjugate base, basically I have a lone pair of electrons that is left because what I lost was Ha. So remember, if this is my acid, when I form H plus, right, these electrons go onto A and make an A minus. So this is that lone pair of electrons that results from the loss of that H plus. To determine if my conjugate base is stable, what I'm actually looking is the stability of that lone pair. Is that lone pair eagerly awaiting a proton to react back to the acid, or is it pretty happy just hanging around and it's not too in a hurry to go ahead and hook up with the H plus? So the more stable that lone pair, the less it's going to be a weaker base because it doesn't have, it's not as reactive as a base. So the more effectively a conjugate base can stabilize its negative charge, the acid that conjugate base came from will be stronger. So the more stabilized my conjugate base, the stronger the acid. There are 4 main factors, and this is called the Areo method, which is listed down here. I'm going to look at the type of atom that carries the charge that has that lone pair. I'm going to look at if that lone pair has got any resonance stabilizing features. Induction is something that we're going to discuss what that is. And then I'm looking at the type of orbital where the charge resides. Is it an S? Is it a P? Is it an sp3? Is it an sp2? Is it an sp? All of these factors are going to help me assess the stability of that negative charge, which will help me figure out if one acid is stronger than the other. So let's look at the atom. Let's say I want to compare butane and propanol. So this is my hydrogen that's going to be picked up by the base, right? So if these electrons go ahead and land on this atom, I have a carbon atom that has a lone pair. This is a carbanion because it's a negative charge on carbon. And I have this oxyanion, which is a negative charge on oxygen. You can try these formal charges. Basically, this is what I have. I have half the bonding, which is 1, 2, 3. It's supposed to have 4. It actually has 1, 2, 3, 4, 5. So it's a -1. And then if I look at this one, 1, 2, 3, 4, 5, 6, half the bonding is 7. It's supposed to have 6. It's also a negative charge. So my negative charge is either on this carbon or this oxygen. So which is more stable? So here's the rule. The larger the atom, the more stable a negative charge will be. Of these 1 and 2 principles here, the size is the most important factor. Here's the other thing. Carbon and oxygen are in the same period. They're in period 2. So they're similar sizes. So if I have similar sizes, I go to principle 2, which is the more electronegative atom will better stabilize the negative charge. Oxygen is more electronegative than carbon. So this is going to be more stable. What that means is that the acid that corresponds to this more stable conjugate base is going to be a stronger acid. So propanol is a more acidic substance. That hydrogen is more acidic than the hydrogen in butane. And all I had to do is look at the type of atom that carried that negative charge when I lost that H+. So I do need to consider the electronegativity of the atom bearing the negative charge. So remember, within a period, the greater the electronegativity, the more strongly its electrons are held. The more strongly electrons are held, the more stable that anion is. The more stable the anion, the greater the acidity of that corresponding acid. So I could look at this hydrogen, this hydrogen, this hydrogen, and this hydrogen. And I can tell by following the pKa's that my acid strength increases as electronegativity increases. HF is the stronger acid because it has the lowest pKa in this series. And that's because F- is more stable than O- or N- or C-. Next, we're going to look at resonance. Resonance can stabilize a negative charge by spreading it out across multiple atoms. This is called delocalization. If my charge can be delocalized among many atoms, that results in a more stable negative charge. So let's look at these two. If I look at ethanol versus acetic acid, right? What I want to do is compare the stabilities of their conjugate bases. So the first thing you have to draw is the conjugate base of those two substances. If I do this, I get this alkoxide where the negative charge is localized on that oxygen, or I'm going to get this guy where if I follow my arrows, this charge is now delocalized because the charge is on both of the oxygens. It's stabilized by this resonance structure that I can draw. So this is going to be the more stable of those two anions. And now I can see that acetic acid, because this is more stable, the conjugate base of acetic acid is more stable than the conjugate base of ethanol due to resonance delocalization of that charge. So this is more acidic of a molecule. All right, next we're going to talk about induction. Now, induction is something you guys have probably not heard of yet, but induction is another way that a formal negative charge can be stabilized. And that's because it also sort of spreads that charge out among different atoms. So inductive polarization of electron density can be transmitted through covalent bonds when I have an atom of an that's nearby that has a higher electronegativity. So let's look at acetic acid. Notice that these are hydrogens attached to this carbon. This is the acidic hydrogen. Notice these are fluorines that are attached to that carbon, and this is the acidic hydrogen. So this is called trifluoroacetic acid. Well, fluorine is more electronegative than hydrogen. So these atoms are more electronegative, and what they're doing is they're pulling electron density away through these bonds from this bond here. So this negative charge that is on that conjugate base has got this sort of pull, right? These electrons are inductively stabilized because the electronegativity of the fluorines is sort of pulling this negative charge this way, which in a sense is going to delocalize it. Notice my negative charge is really localized on those two atoms in acetic acid based on the electrostatic potential map. But now this is much less red, which indicates that that charge has been sort of delocalized through the bonds by this inductive polarization of electron density. So if I look at this, any electron withdrawing atoms or groups that are near an acidic hydrogen can affect the stabilization of that conjugate base. So let's look at acetic acid versus this guy. Now this is trichloroacetic acid. So now I'm looking at hydrogen versus chlorines. In terms of electronegativity, chlorine is still much greater than hydrogen. So because this is going to be sort of stabilized when I make that negative charge, right? That negative charge that's going to reside on that oxygen is going to be stabilized through induction. So this is going to be the more acidic compound. Now, the more electron withdrawing groups I have, the more stable that conjugate base. The higher the electronegativity, the more stable that conjugate base. And the closer that electron withdrawing group is to the negative charge, the more stable the conjugate base. So I'm going to compare this to acetic acid, which just has hydrogens on the end. This guy has 2 hydrogens and a chlorine. This guy has 2 chlorines and a hydrogen. And this guy has 3 chlorines. Notice this trend in the pKa. As I go across here, I'm increasing acid strength because the pKa is decreasing. So this is much more acidic because of this inductive stabilization. The inductive stabilization is greater when there's 3 chlorines versus 2, and then when there's 2 chlorines versus 1, and then when there's 1 chlorine versus 0. I can also look at the O of a Rio, which is the type of orbital. This can also affect the stability of a formal negative charge. And that's due to this principle. The closer the electrons are held to the nucleus, the more stable they are. So let's think back to the difference in the orbitals of an sp3 hybridized carbon, an sp2 hybridized carbon, or an sp hybridized carbon. This is a shorter atomic orbital. That means any electrons in here are going to be closer to the nucleus. So when I look at this, right, this can greatly affect the stability of the conjugate base. Is my negative charge in my, are my electrons in an sp3 orbital, an sp2 orbital, or an sp orbital? So let's look at this. I have got a long molecule. This is an alkene. So this is an sp2 hybridized carbon, and this is an sp2 hybridized carbon. This is an alkyne. So this is an sp hybridized carbon. This is an sp hybridized carbon. So let's compare the acidity of the hydrogen that's attached to the carbon in an sp orbital, or the hydrogen that's attached to the carbon in an sp2 orbital. So let's take off the red proton and draw the conjugate base. And then take off the blue proton and draw the conjugate base. So now I have to figure out which of these carbanions is more stable. Remember, this is in an sp orbital, this is in an sp2 orbital. So the lone pair in an sp orbital is closer to the nucleus, which is positively charged. So this is stabilizing. This sp orbital is shorter. Those electrons are closer to the nucleus, which is positively charged. That positively charged nucleus will stabilize the negative charge, more so in the sp orbital because it's closer to the nucleus. So this proton is more acidic than this guy based on the type of orbital that that pair of electrons is left in. So if I look at an alkane versus an alkene versus an alkyne, and I think about these are sp3 versus sp2 versus sp hybridized carbons, notice the sp3 is the longest orbital and it has the highest pKa. So this is definitely the weakest acid and this is the strongest acid. Now, don't get me wrong, these values are not very strong. I mean, it's not like I take acetylene and I can do an acid-base reaction like if I have HCl. This is still a very weak acid relative to HCl or H2SO4 or a lot of other ones. My carbon-based carbanions are actually pretty hard to make. I need very, very, very strong bases, even in this case. But when I compare the orbitals themselves, the alkane in an sp3 orbital, that when that proton leaves, that is going to be least stabilized, which is the weakest acid. So I'm going to generally use a Rio if I don't have my pKa chart. I look at the atom, then I look at resonance, then I look at induction, then I look at the orbital. And it's actually typical that I look at these different features in this order: atom, then resonance, then induction, then orbital. But note, with every rule, there are also exceptions. So if I look at this, right, a Rio is a guideline, and sometimes it fails. For example, here's my alkyne. This is an amide base, right? Here's my acid, which is going to be more acidic. So this is stronger. And here's my conjugate acid, which is going to be less acidic because my pKa is higher. If I had judged the conjugate base stability, so like we know this actually happens, the equilibrium lies to the right. And we know this because I know the pKa values. This is the weak side. If I had judged this based on a Rio, right? If I had looked at this based on a Rio, we would have concluded that the negative charge on nitrogen is more stable than carbon. And we would predict that this equilibrium lies to the left. And we would have been wrong. So for some acids, we simply need to know the pKa values because there are exceptions to the rule. But as beginning organic chemists, you should know how to do this analysis so that if you don't have your pKa chart available, or on a test, if I ask you to use the Rio method to explain what you see on a pKa chart, you will need to know how to do this. So here's some examples. Predict which proton, the red or the blue, is more acidic in each of these compounds. So I'm going to look at this versus this. So when I draw the conjugate base, what I'm going to look at is this more stable or is this more stable, right? So this is on a carbon, this is on an oxygen. If I use the Rio method, here I'm looking at the atom, and what I'm going to see is that this is going to be more stable, which means this is going to be more acidic. Let's look at these two conjugate bases. I could have this guy versus this guy. Notice my atom are both carbon. So I can't use the atom in order to do this. So let's look at resonance. I have resonance that goes this way. And I have resonance that goes this way. So I have two resonance stabilized structures in this particular case. Here, I only have this resonance. So this hydrogen has two resonance, actually three resonance structures, and this one only has two resonance. This is more stable, so that hydrogen is more acidic. Okay, I'm gonna leave that there. You can try the other one. And actually, I'm gonna let you go through those in practice. I do have the answers on those, so hopefully that will help go through these. Now, when I predict the equilibrium position, what I'm going to do is I'm going to look at any acid-base reactions. And I'm going to look at the pKa values of HA and HB. So I look at this and I look at this. The higher pKa will be favored because this would be the weaker acid. Or I'm going to compare the relative stability of the bases. And then remember, the weak side is always favored. So I'm going to need to be able to assess these different molecules according to their acid strength, because to predict the equilibrium position, I have to determine which one is weaker, and then the equilibrium will lie to the weak side. All right, one last section in this acid-base chapter. There is another definition of acidity and basicity. There's also the Lewis definition. So a Lewis acid, here's the difference, accepts a pair of electrons. I'm looking at lone pair here. I'm not looking at H+. I'm accepting a pair of electrons, and the Lewis base donates a pair of electrons. So acids under the Bronsted-Lowry definition are also acids under the Lewis definition. Bases under the Bronsted-Lowry definition are also bases under the Lewis definition. But this now has a different perspective because I'm looking at where this lone pair is. So here is my lone pair. This is going to donate a pair of electrons. So this would be the base. This is going to accept a pair of electrons. So this would be the acid. Typically, what I get is this sort of a complex where I have a new covalent bond formed in this Lewis acid-base reactions. The electrons in this bond were donated by B, and now they're shared between the two atoms. Sometimes that gives me this positive negative sort of separation within the same molecule. When HCl dissolves in water, The strongest available Lewis base is a water molecule, right? And then this is going to be the proton transfer reactions. This is donating this electron pair, and this is accepting an electron pair. So this is the Lewis base, and this is the Lewis acid. Again, it's a little bit different perspective from the other two acid-base theories. What's nice about the Lewis acid-base theory is it does extend to other types of atoms. I don't have to be in an aqueous solution. I can actually look at other things. When we talk about various catalysts for electrophilic aromatic substitution, we're actually going to look at Lewis acids and bases and how they actually help reactions proceed. But for now, we just need to be able to recognize Lewis acids and bases. Methanol is acting as a Lewis base here. The HCl is acting at a Lewis acid. And what I'm going to get here is this protonated methanol. Remember, I'm forming this bond and I'm breaking this bond. And what I get is this oxonium ion, which is basically a protonated methanol when this reaction occurs. Here are some examples of organic Lewis bases and their relative base strength. So you can tell that I have very weak bases over here, and I have very strong bases on that side. And notice that I either have charges or lone pairs that are giving a charge. So I'm always looking at the lone pair, right? That lone pair is what is being transferred in Lewis acid-base theory. Another type of Lewis acid we're going to encounter later is something called a carbocation, which is an organic cation in which a carbon bears a positive formal charge because it only is bonded to 3 different atoms. When this happens, that carbocation is looking to accept a lone pair. So it's looking to act as a Lewis acid, and then my Lewis base is going to donate a lone pair in order to form the new bond here. So this is going to be my Lewis acid because it wants to have a lone pair in order to fulfill its octets. Some Lewis acid-base reactions cannot be classified using Bronsted-Lowry. For example, this boron actually has an empty p orbital, which is going to actually accept a lone pair. So this is going to be the Lewis acid. This is going to be the Lewis base. This has an empty p orbital, which is set up. If I look at this, remember, this is sp2. So what I have is that trigonal planar with my empty p orbital. When this is boron, I have my fluorine, but that p orbital exists, but it's empty, waiting for a lone pair. So when a Lewis base is around, it can donate its lone pair into this empty p orbital. Notice I do get a formal charge. The oxygen, right, here's my lone pair that formed that bond to boron. My oxygen becomes plus, and my boron becomes negative. And I will have to represent those formal charges in this as well. We will be looking at this a lot more carefully later on, but at the moment we are done with chapter 2. We are done with acids and bases. So the next topic we're going to cover is starting on chapter 5, which is addition reactions to alkenes. And we're going to start looking at reaction mechanisms, which is probably one of the most interesting and one of the scariest topics in organic chemistry. So we will get to that later.